Okay. We will talk about the 19th lecture today on module 1 on dynamics of ocean structures. Today we will discuss a new numerical method which is given by stored law, which is applicable to elastic systems as far as multi degree of freedom system is concerned. The one main advantage the system has, or this method has, is it will give you the fundamental natural frequency of the system automatically and the mode shape. It will give you a pair. So, this will give you the fundamental frequency and the corresponding mode shape. And in this example, in this class I will show you, I will pick up an example and demonstrate that I will solve the problem by all the 3 methods, namely stored law, which I will explain here, influence coefficient method, which I will again explain, and Dunkerley method. You will see all of them are highly comparable and get the same answer in all the 3 cases. So, this method is very interesting, easily computer programmable. It is not problem specific, it is highly generic. This method has concept based on the proportional displacement of the mass points. In fact, to be very specific, we can say of the lumped mass points under inertial forces. So, you have to assume a proportion of displacement between the mass points and try to converge it. So, again you will see this method has got a very good correlation and understanding between with that of the influence coefficient method. Even in influence coefficient method also you actually assume the displacement vector and try to iterate the vector for its convergence. This method also exactly do the same thing, but it does slightly in a different manner. We will see how it can be done. This can be applicable to elastic systems, on the other hand the displacement offered by the system is not very large. Okay. So, let us take up a problem and demonstrate this method step by step. So, the problem is the basic problem what we will have here, which I will demonstrate in all the 3 methods. So, let us say I have a spring mass system. So, I have 3 mass points, let us say m1, m2 and m3. Let us say k1, k2 and k3 are the stiffness of the springs, and the degrees of freedom are marked here as x1, x2 and x3 as shown in the figure. Just for our understanding, we will keep k1, k2 and k3 same. I will do another problem where they are varied, okay, just for understanding, and let m1, m2 and m3 be same as m, okay, for this problem. But I will take another example where this is 4k, this is 2k and this is k. We will just see how it can be easily handled, there is no confusion. So, we will demonstrate the Stored-Law's method by assuming a proportional displacement between the mass points at respective degrees of freedom. Let us try to find out what will be the restoring force offered by these respective springs to the respective mass points in the respective degrees of freedom, and try to see whether these vectors assumed in the beginning of the iteration are getting converged. There is a mathematical proof available in the literature that stored law will converge to the natural frequency and mode shape. Okay. So, there are 2 issues, one is the Dunkerley's and the other is stored law. We will derive this after we understand the method later. Okay. There is a mathematical proof available where stored law will converge to the fundamental of the lowest possible frequency in the corresponding mode shape. We will talk about that proof later. First let us understand the method. So, the method goes as a tabular form. Let us try to draw the tabular form here. Let us say assumed deflection Let us say the mass, the stiffness points are K1, M1, K2, M2, K3 and M3. In this case they are all going to be Ks and Ms. Okay, let us write down the values here as such. Now I want to assume the deflection at the mass points, because I am always arguing about the proportional displacement of the mass points. Okay. So in all these examples there is a commonness. The commonness is the degrees of freedom are generally measured at the point where the mass is lumped. That is a very common practice in dynamics. Okay. So since we do not know the proportion of the mass, that is what is the proportion of M2 and M3 versus M1, I mean which is heavier, we have no clue. Let us assume that all of them are going to be displaced by the same proportion, which may not be correct, but only one catch here is all of them are positive. It means I am looking for the fundamental frequency. Okay, I am not allowing the change of sign or a zero crossing in the mode shape. So I do not know, I will start with 1 1 1. So let us say the inertia force. Mx double dot is the inertia force, x double dot is omega square xi for a given harmonic excitation, which already seen except for the change in sign, that is out of phase. Acceleration and displacement will be out of phase because they are displaced by minus signs, they are out of phase. So look at the absolute value, we are looking only for the proportional displacements between the mass. Okay, we can look for the absolute value because all of them are going to be negative, we need not have to look at the negative sign. So I should say now as omega square m of 1. Omega square displacement is the acceleration, minus sign I am not considering, m is this m. Strictly speaking this should have been m3, okay, but since m3 and m are same I am writing simply m. Similarly omega square m of 1, omega square m of 1. This 1 is this displacement. Had I have 1 2 4, I would say 4 2 1 here, so on and this. Let us try to find the spring force. Mass m3 is the last point which is extended from the system. So let us start from the spring K3 here. So simply say this is my spring force which is omega square m. Then when I go to K2, the spring force of K3 will also get added to it. Okay. So 2 omega square m, 3 omega square m. Once I have the spring constant K, I have the spring force F, I can easily find the spring deflection which will be 3 omega square m by K1, but it is K. So I can write m by K outside here, I can simply say it is 3 omega square. Now you may ask me a question, sir, here the masses are all 1 1 1, K is all 1 1 1 or K. So you are able to take out a constant here. What happens if this is m, this is 2m and this is 4m and this is K, this is 4K and this is 6K, still m by K can be taken out, that multiplier can go in. On the other hand, it is very important for us to establish the proportional mass of m2 and m3 in terms of m1 all the time. Okay. Similarly, the proportional ratio of K2 and K3 in terms of K1. It means I have a common multiplier This is only to facilitate the units of iteration. If you have a larger unit, iteration becomes difficult, okay, just to facilitate, because mass and K values will be very high in the real problem, right, 10 power 6. So, we need not have to have a multiplier of this order here, we take it out, keep that value as a multiplier, we can use it later, okay. So, get only the proportional inside. So, K has gone here. Similarly, this will be 2 omega square, this will be omega square, okay. M by K has gone out. Now, I want to find the calculated deflection. Let us say M by K is available here. When I start doing the calculated deflection, I will start from the first degree here, because the deflection of the second and third degree will be cumulative from the first, okay. So, start from here. So, this is going to be 3 omega square, M by K is available anyway here, then add this and take it here as 5 omega square, add this and take it here as 6 omega square, okay. Now, I have assumed a deflection of 1 1 1 of the mass point, I got a deflection of something as 3 omega square, 5 omega, 6 omega square, okay. I want to find the proportion of this, because this is also a proportion only. If I say this as 1, this will be 1.67, this will be 2. Let us go for a 2 decimal convergence, you can also go for n number of convergent digits, okay. So, this becomes my assumed deflection for the second iteration. Why I am banding this? Because we started with 1 1 1, it is not converging at 1 1 1, it is coming to be 1 1.67 and 2, okay. They are not converging. So, I have to go for a next iteration. So, can we repeat the same set of procedure again here? Let us try to fill up the table. So, I have inertia force here, I can take multiplier m out. So, this should be 2 omega square, this should be 1.67 omega square, this should be omega square. I have taken m out here, then I can work out the spring force. Let us say again m out. So, this is going to be 2 omega square, 3.67 omega square, 4.67 omega square. I want to find the spring deflection. I take m by K out here. So, 4.67 omega square, 3.67 omega square, 2 omega square. Now, I want to compute the calculated deflection, m by K constant out here, 4.67 omega square, (8.34), (10.34). I want to find the ratio of this, 1.785, let us say 79, 2.21. So, we started with 1.67 and 2.0, but we landed on 1.79 and 2.21. So, this is again banded. So, let us do one more iteration. Kindly fill up the third scheme. This is 3, this was 2, and of course, this was 1. So, inertia force, spring force, spring deflection calculate the deflection so 2.21 omega square 1.79 omega square so 2.21 omega square 4 omega square 5 omega square, let us say 5 omega square, 4 omega square, 2.21 omega square, 5 omega square, 9 omega square, 11.21 omega square, the ratio becomes 1.80, 2.24. One can verify this data once again back by putting this and see in the fourth case you will get back the same value as 1.8, 2.24. You can otherwise also see here this is converging, this is more or less equal to this, the second digit is only the variable, the first digit is converging. So, it will converge. Now, let us quickly look at the discussion of this particular table. Now, let us look at the crooked points where we can go wrong, in making the table. You should always enter the table in the same format as x1, x2, x3. On the other hand, x1 with k1 and m1, x2 with k2 and m2, x3 with k3 and m3. Therefore, x1, x2, x3, that is the first order which you will follow. The second order will be always m and k should be expressed as a ratio. You must take m and k common out and enter only the proportional values of m and k here. The third, which is very tricky. Now, at 1.67 and 2 at the second iteration, if you have rounded off this to 1.7 let us say and did, you will never get convergence. You have to maintain the value as it is. Okay, no truncation should be done at this level for the next iteration, never. Try to continue with the same value as it is. Okay. And the fourth very tricky difficulty is spring deflection, calculated deflection. There are two deflection terms here. One is entered at the mass values, one is entered at the stiffness values. That is why I am deliberately writing this is spring deflection, this is deflection of the mass point. Please understand, both of them deflection only. One I am writing only at the location of stiffness of the springs, one I am writing at the location where the mass is. You are always finding the proportion of the mass, but not the proportion of the stiffness of the springs. Please understand this, both are deflections only. Okay. This is another problem where generally people make a mistake. Now, from this how do we get omega, that is a very important issue. Okay. Now, the original deflection is actually not 1.8 and 2.24, it is actually 5, 9 and 11.21 omega square m by k, which are converted to ratio of 1, 1.8 and 2.24. It means, if the frequency of the mass 1 is 1, mass 2 is displaced by 1.8 times of that of 1 and 2.24 of that of mass 1 at a specific omega. Okay? That is the meaning of this. Therefore, these two values should be connected by the multiplier of m by k and omega square. Okay? Let us do that here. So, 1 plus 1.8 plus 2.24 should be equal to 5 plus 9 plus 11.21 of m by k omega square. So, let us get omega, some value of k by m. How much is this value? Let us say very specifically, is it 0.48 or 0.447 something? K by m. So, this is my fundamental frequency and the first mode shape is 1, 1.8, 2.24. This is what I got by Stokes law. As you know, in engineering practice it is very simple. If you are proposing a new scheme of iteration or any numerical algorithm, you must always show the validation of this algorithm with respect to the established existing algorithm. There is always a practice in engineering. When stored law was introduced, already inference coefficient method and Dunkerley method were in existence. So, one has to actually compare these values with both of them, which we will do now. Okay? We will see how they are comparing. You may have a question in the exam that a table of this order is given to you with convergence, omega and phi are given to you, some of the values in between are erased, you have to fill up that. If you know this table thoroughly, you can do that, otherwise you will not be able to. Okay. I will just remove some of the values in between the table for a 10-degree freedom system problem, let us say, which you cannot imagine by easy calculation unless you know the procedure. So, that is why I am telling you, please follow the table carefully, how the hierarchy was developed and what is the reason why we started from the third x3 and then came to x1, because there is a cumulative deflection of the spring. Okay. That is how it is done. So, now I want to calculate the fundamental frequency, but not the mode shape from Dunkerley. So, I must have the delta matrix with me. Okay. I can directly derive the alpha matrix, which is also useful for influence coefficient method. From that I can pick up the diagonal elements, I can also find Dunkerley's frequency from that. So, let us try to derive the influence coefficient directly, that is alpha ij. Alpha ij is otherwise called flexibility matrix, where for unit force we are trying to find the displacements at different degrees of freedom, keeping all of the degrees of freedom constrained. So, to derive alpha ij, which are called influence coefficients. We already given in algorithm in the last class, let us try to derive the alpha matrix directly. There are two ways of doing this. One, you can convert them into equivalent springs and keep on deriving, which is a lengthy procedure. We can directly derive alpha ij by forming an algorithm as we discussed in the last class. Let us try to do that, because I did that problem slightly faster in the last class. Let us repeat that for this particular example, so that let us understand how this was derived. So, this is my first degree, this is my second degree, this is my third degree. Let us say we will keep all of them as k's and all of them as m in this example. Okay. So, let us apply unit force here. Unit force, I am talking about alpha ij. For stiffness, unit displacement. Okay. Here it is force. The moment I try to apply unit force here, please watch carefully here, because if you are able to understand this, I think the first module essence is completely understood by you, because it is very difficult for you to understand this otherwise. Please understand this carefully here. So, when this mass is moving down by an unit force, this spring will try to push the mass up. So, I mark the arrow in this fashion. So, it is always marked as a pair. Okay. When this mass moves down further, again this spring will try to push it up. So, I am marking it as a pair. When this mass goes down, this spring will try to pull the mass up, I am marking it here. Of course, here there is no displacement, it is a fixed line, I do not need any connection here. So, this value will be alpha, okay, the stiffness of the spring multiplied by the displacement, which is alpha 1 1 minus 2 1. This is going to be stiffness of this spring alpha 2 1 3 1. This is going to be stiffness of the spring alpha 1. So, the second subscript here will all be unity, indicating that we are given unit force at the first degree of freedom. The first subscript here will all refer to the respective values of degrees of freedom accordingly to where we are measuring it. Similarly, let us do the same procedure here. Unit force here. So, when this mass is moved down, this spring will try to push it up. So, it is always marked as a pair. When this mass moves down, this spring will try to push it up, always marked as a pair. When this mass moves down, this spring will try to push it up. So, this is going to be k of alpha 2 2 minus 3 2, alpha 2 2 minus 1 2, k of alpha 1 2. The second subscript all will indicate 2, showing that we are given unit force at the second degree, and the first subscript all will refer to the respective degrees of freedom as we are measuring the forces. Similarly, the third one, give unit force at 3. When you try to pull the mass down, this spring will try to push it up. So, always mark it as a spare. Similarly, when this moves down, this pushes up, mark it as a spare. When this moves down, this will push up. So, stiffness of this spring multiplied by stiffness of this spring multiplied by stiffness of this spring multiplied by okay. This is 1. So, I want to write the force equilibrium equations for this. Let us do it here. Let us pick up this k of alpha 1 1 plus k of alpha 1 1 minus 2 1, that is this. These two should be equal to 1. Why? Because these two forces for this mass point are upward, but this is downward. Similarly, here k of alpha 1 1 minus 2 1 should be equal to k of alpha 2 1 minus 3 1. These two, they are opposite, and here k of alpha 2 1 minus 3 1 should be set to 0 because there is no other force. So, k cannot be 0, therefore, this is 0. This implies that alpha 2 1 will be equal to alpha 3 1. Substitute that back here, this term goes 0, which means k cannot become 0, therefore, alpha 1 1 will be equal to alpha 2 1. Substitute this term here, this term goes 0, alpha 1 1 will be 1 by k. Okay. So, I am now getting 1 1, 2 1 and 3 1. The first column I have got, okay, all will be 1 by k. So, let me write down the matrix here, alpha matrix. Similarly, let us do it for the second one. Let us pick up here k alpha 1 2 should be equal to k alpha 2 2 minus 1 2. I am talking about these two. Then here k of alpha 1 2 minus 2 2 plus k of alpha 2 2 minus 3 2 is 1. Then last k of alpha 2 2 minus 3 2 is 0, which implies that k cannot be 0. So, alpha 2 2 should be 3 2. Substituting back in this equation, this term goes away because they are equal. So, again alpha 1 2 minus alpha 2 2 is 1 by k. I am substituting it here, alpha 1 2 minus alpha 2 2 is 1 over k. I substitute that value here. So, can you give me the value of alpha 1 2 and alpha 2 2? There are two equations now here. I will substitute this back here. I know alpha 2 2 is alpha 3 2. Can you give me alpha 1 2, 2 2 and 3 2? Because if I know these two, this can be equal. So, this is 1 over k, this is 2 over k and 2 over k. Am I right? So, let us write down this as 1 over k, 2 over k and 2 over k. Similarly, can you get me the value of the third column, writing the force equation for this third case, third column. So, it is going to be 1 by k, 2 by k, 3 by k, am I right? So, Dunkerley says so, here the mass points all m1, m2, m3 equal to m, and delta is nothing but 1 by k. So, 1 by omega square will be equal to only the leading diagonal elements, because I the leading diagonal elements only. So, 1 plus 2 plus 3, which is 6 m by k. Can you find what is omega n? 0.41. What is the third decimal? Okay. So, this is more or less verified. Let us quickly do this for influence coefficient for first degree alone. So, alpha matrix is available here, 1 by k of 1 1 1, 1 2 2, 1 2 3, and mass matrix is m 0 0 0 m 0 0 0 m. Can we also m of, let us say, 1 1 1. So, x 1, x 2, x 3, alpha 1 1, 2 1, 3 1, alpha 1 2, 2 2, 3 2, alpha 1 3, 2 3, 3 3, m 1, x 1 double down. That is the algorithm. Then I can replace the inertia force as an equivalent displacement force as omega square xi, I get a vector. I write directly the control matrix. The control matrix now is going to be x1, x2, x3, which will be equal to omega square m by k Let us start with the first iteration as 1 1 1. And get me the multiplier of omega square m by k of the vector. The multiplier is 3 and 1.672 and so on. Let us continue. You will see that there is a very close agreement between this vector with influence coefficient method with that of Stored law. Exactly it will be same. Okay, just converge, you will see as you proceed, you will get the final vector as 1.82.4, 2.24 sorry, with a multiplier of 5.04 omega square m by k of 1.82.24. So, I can now read 1 is equal to 5.04 omega square by k of 1, which gives me omega as, and the phi value is and this value is going to be how much? So, this value is going to be 0.445. So, this is Dunkerley and omega n is 0.445 k by m and phi 1 is 1.8, 2.24 is exactly same as that of Stored law, and this is exactly same as that of Stored law. So, there is a complete convergence and matching between the three methods. In the next example, next class we will take up one more example of 4 degree of freedom system model and again demonstrate the problem with Stored law and influence coefficient method Dunkerley. You will see that this method will be very promisingly converging for higher degrees of freedom. Okay. Now, Stored law is considered to be one of the most effective tool of finding the fundamental frequency and the mode shape, which has superseded the use of Dunkerley, because Dunkerley had only one difficulty, it does not give me the mode shape. Now, there is a very interesting question asked to you, why Dunkerley cannot give me the mode shape, what is the problem? Okay. So, that is a very interesting question, you have got to answer that, why Dunkerley is not focused on mode shape. Okay. And influence coefficient method and Stored law are comparatively matching, but Stored law is more popular because Stored law focus only on the fundamental frequency and mode shape, and its method is highly generic. Okay. And convergence is guaranteed, it is very fast, and higher modes if you are not bothered about, one can easily find the lowest possible mode with Stored law. Now, I already said you that the influence coefficient methods convergence or the time taken for iteration closely depends on what is the vector you have assumed for iteration scheme here. This is true in Stored law also, okay, but the convergence of Stored law will be much faster. Why? Okay, two questions. Why Dunkerley is not focused on mode shape, and why Stored law, though is also dependent on the displacement proportionality of the mass points, but still Stored law will converge faster than influence coefficient method. Why? There is a problem in the algorithm. Please look into that and see, tell me what is the answer for this. Any doubt here in 3 methods now? We have got 3 methods now, I will have another 2 more methods subsequently discussed in the next classes. So, you will have 5 methods, there are around 7 methods available in the literature, out of which we have spoken about 5. I already given you the eigensolver also, if you include that as also a method, we have got 4 methods now available on hand to solve any multi-degree freedom system problem in general. Okay. 3 and eigensolver classical, 4 methods we have, I will have 2 more methods, Rayleigh, Ritz and Holzer. So, 3 more around 6-7 methods are available on hand, you can use any one of the methods to find out omega and phi. Okay. Any doubt for anybody in this particular algorithms, all the 3. So, you must practice the problems by taking more number of let us say spring mass systems and note down the time, how much time you take. So, on an average you should not exceed maybe about 10-15 minutes to solve a single problem. If you have been asked to solve all the 3 mode shapes and frequencies in influence coefficient method, or maximum 5 to 7 minutes by hand, if you want to find out only the fundamental frequency in the mode shape, that is the time limit. Okay. You must train yourself to solve these problems by hand using calculator within about 5 to 7 minutes for 3 degree freedom system problem. Okay. So, try to have a practice on these problems, and there are many numerical available in the textbooks. Try to put your idea and thoughts on that, try to solve them, and try to answer those 2 questions what I asked, why Dunkerley is not giving the mode shape and why Stored law is converging faster than influence coefficient method. Okay, thank you.